Hello, everyone. It's once again a pleasure to meet you online at the Long Range Colloquium. To those of you who are joining for the first time, this colloquium is run by the Virtual Science Forum, a volunteer organization with the goal of accommodating online events of essentially any kind. It's open to everyone to both attend and organize and host their own events. But today we are happy to have Andrea Young from UC Santa Barbara. He will tell about orbital magnetism in graphene heterostructures. If during the talk you would like to ask a question, please use the raise hand feature and I will keep an eye on chat and I will invite you to ask your question. But please do not hesitate. Please, Andrea.
Okay, thank you, Anton. Yeah, please just interrupt if you have a question. So thanks again for the opportunity to present some recent work over the last couple of years from my group. I'm going to tell you about our various explorations of orbital magnetism in a variety of graphene heterostructures. So let me start with a sort of a slightly cheeky history of ferromagnetism and its exploration by our species. So the first reports, at least in the West, of ferromagnetism go back apparently to Thales of Miletus, who was a pre-Socratic philosopher and who noted the attraction of iron by magnetite. He know for sure because none of his writings survive, but the report from later writing a century or two later was that he concluded from this that matter is actually alive because magnetite could have iron. Now, our theory of magnetism has improved since then. So in particular, sort of maybe important result is that actually it was Niels Bohr's PhD thesis, also known as the Bohr-von-Lewin theorem, which noted that classically the free energy is independent of the vector potential, which means that the magnetization, which is the derivative of the free energy with respect to the magnetic field, has to vanish. And as a result, finite magnetization has to be a quantum effect, and there's no classical magnetism. So there's a simple way to see this. It's actually an exercise in Landau and Lifshitz quantum mechanics, deriving the exchange interaction in a pair of finite potential wells. So if you put two particles in two finite square wells, you can calculate the effect of the Coulomb interaction by putting particles in either a symmetric or anti-symmetric combination of, say, the ground state wave function of these two wells. And you'll find that there's actually an energy splitting between the symmetric and anti-symmetric combinations of those two wave functions. They're split by this Coulomb repulsion, and that depends on the details of, say, those wells. But if that J, which is the difference between the symmetric and anti-symmetric orbitals or anti-symmetric and symmetric orbitals is negative, this should be a minus sign, apologies, then the anti-symmetric orbital wave functions are favored, and as a result, the orbital wave function should be anti-symmetric. And because if you're thinking about electrons, their total wave function must also be anti-symmetric, that means their spins should be symmetric, and you favor a state with a finite polarization. This was expanded on by Heisenberg in his model for spins, and in 3D, a model like this, where you basically, that exchange gives you some effective coupling between spins. It's an orbital effect. It's not really a spin-spin coupling, but it's an effective spin-spin coupling, supports a ground state with a finite large magnetization. Now, in 2D, as we know from Merman-Wagner theorem and so on, to get true long-range order, you need some anisotropy. A 2D Heisenberg model won't give you won't give you a phase transition. So you need to restrict those moments to lie, let's say, out of the plane. And if you do that, then you get the 2D Ising model, which of course does have a phase transition. And so the way this is typically accomplished in materials is to use spin-orbit coupling, which allows you to endow the spins with some anisotropy, so they may prefer to be out of plane rather than point in arbitrary directions, even if they all want to align with each other. Now, in solids, you have kinetic energy, right? You're not just in a finite, a small state like a molecule. You have kinetic energy, and as a result, polarizing ferromagnetically actually has to compete with that kinetic energy. And so Stoner pointed out that this was going to happen when the bandwidth was small enough as compared to this exchange coupling. That basically, if exchange is sufficiently strong, then you will favor filling, let's say, this whole band or some portion of this band in an imbalanced way with respect to spins, but that competition fundamentally comes from the interplay between exchange J and bandwidth gamma. And that gamma is simply proportional to 1 over density of state. So this so-called Stoner criterion gives us the crude requirement for ferromagnetism in the solid. Now, graphene, which is what I'm going to tell you about today, is a rather unlikely magnet based on these considerations. So first of all, it's very 2D. So already you're fighting with Merben-Wagner. The orbitals in graphene are very delocalized in monolayer graphene to start with. And there's no spin-orbit coupling. So it would seem to fail in almost every important respect based on what I told you. But as I'm going to show you today, this turns out to be something that you can control experimentally. And in fact, you can get over all of these problems in their own way. And the most key point that I want to emphasize about the graphene band structure, I think many people in the audience are surely very familiar with this. I see some of the discoverers of this fact in the audience as well, that in graphene, the key element is the valley degeneracy that is sort of inherent to these honeycomb systems. So in particular, the low energy band structure in monolayer graphene, and indeed in all of these honeycomb-based compounds is, and heterostructures, has more or less identical electronic structure at the two distinguishable corners of the Brillouin zone. And most of what I'm going to tell you about today ultimately comes down to the fact that this valley degeneracy functions as an anisotropic microscopic degree of freedom that can take the place of electron spin to give you magnetism in a system with no spin-orbit coupling. And that by controlling the band structure, you can essentially deal with this issue of delocalized orbitals and make the orbitals much more localized, and as a result favor magnetism. And that magnetism is fundamentally not based on electron spin, although it may involve electron spin. And as a result, you can build some new types of magnets which have a variety of properties, which I'll tell you about in the next over the course of the next hour. So let me tell you about the talk. Let me just outline that talk. So this is not a history. It is not a chronology, certainly. It is a personal trying to put a pattern of facts that we have discovered and many others in our community have discovered in these types of materials. So it will, if anything, start achronologically by talking about some unpublished results on rhombohedral trilayer graphene, where I'll tell you about what I think is an extremely straightforward model for an itinerant spin and valley ferromagnet in a graphene system that is more or less described by a Stoner model. I'll talk about how what you can get by introducing a moire pattern, so a superlattice potential that allows you then to have, in particular, energy gaps at finite density, which correspond to commensurate fillings of that moire lattice. I'll tell you about some of our work on understanding the microscopic picture for pinning and dynamics in moire churn insulators. So in particular, some work on twisted bilayer graphene and mapping of how magnetic domains of these orbital magnets are pinned in those systems. And then finally, discuss a little bit some of the new electrical field based control knobs that you can get in these orbital magnets, focusing on yet another moire type system. So again, for some basic review, right, monolayer graphene is not a good candidate for a magnet. In particular, it has a density of states that is very low, close to charge neutrality. It grows with density, but only weakly. But already by stacking a second layer, you can modify that quite a lot. And so the band structure of Bernal Bilayer graphene is already different. In the simplest picture, you have touching parabolas, which have a constant density of states. That's better than a vanishing density of states, but still not fantastic from the basic point of view of wanting to increase density of states as much as possible in order to favor magnetism. But as has been known for many years, at this point, when you apply an electric field across Bernal bilayer, you modify that band structure quite a lot. And in particular, you generate band minima at that are particularly flat. So in particular, the electronic structure of bilayer graphene, roughly speaking, gives you a quartic band minimum and band maximum with a tunable gap. And if you calculate the density of states for a quartic minimum in 2 dimensions, you'll find that the density of states, in fact, diverges like a 1D Van Hoff singularity for parabolically dispersing electrons as you approach charge neutrality. And so the prediction from this diverging density of states, which was made explicitly by Castro et al. In 2008, is that you should have ferromagnetic states at low density in gapped bilayer graphene, and that should be relatively straightforward. And there are, of course, analogs of this in semiconductors. There's a long literature on the ground state of a 2-dimensional electron gas at very low density that finds a variety of ferromagnetic and Wigner crystal states, and there are observations of this type of physics, for example, in silicon MOSFETs and recently in 3-5 semiconductors, where signatures of ferromagnetism has been seen. A key element here is that all of this is predicated on having a very clean system where you can control, where in fact these calculations of the density of states are not broadened by disorder. Disorder in general, if you have a very high density of states, will serve to spread that out by changing the energy of states at different positions in your system. You'd like to avoid that. So that's sort of a sine qua non of exploring this physics. So let me tell you briefly, I think, again, many in the audience extremely familiar with this, but how we've approached that problem. So we make our samples by a sort of, at this point, totally standard in the field technique, where you pick up 2D material with some kind of polymer. It depends on the day which type of polymer one uses. This is what the process looks like, picking up here a hexagonal boron nitride flake, and then one can make these complicated heterostructures more or less at will with sufficient persistence. The key enabling technologies for us have been this sort of march over the last decade or so towards cleaner and cleaner samples, and in particular, the removal of what has become clear, although I think it's been clear already for many years, is that graphene itself is just a fantastic material. It comes to us in a sense out of the ground, or at least out of a blast furnace of a steel mill, nearly perfect. And one, as an experimentalist, has to preserve that perfection. And the way where that has gone has been to develop structures where everything is made out of a van der Waals material, hexagonal boron nitride being the sort of other important one, which is an insulator. And the graphene sees only boron nitride graphene interfaces, which have this marvelous property where they are self-cleaning. So under some strain, impurities will move out, but they cannot move back in. They effectively make a good seal. And they only see also as gates single facets of 2D materials. And this was something that we understood just a couple of years ago and has enabled us to really make exceptionally clean devices. So for comparison, when we do careful experiments on, say, fractional quantum Hall physics, which I won't discuss here today, we find Landau level broadenings on the order of 8 Kelvin. That's comparable, a little bit worse than what's achieved in kind of top of the line gallium arsenide 3-5 semiconductor wells, where in samples with mobilities on the order of 10 million, one finds broadenings of, let's say, 2 Kelvin. So this is somewhat worse, but it's sort of in the same ballpark. The experiment I'll tell you a fair amount about in the first part of the talk that we like to use, because it avoids some of the problems arising from physical edges that bedevil some transport experiments. I'll show you many other transport experiments later. Also, is to measure the penetration field capacitance. So this is done by using graphite top and bottom gates here as sensors, so that you can just measure how much electric field from a bottom gate penetrates through to the top gate, which gives you a measurement of the density of states directly of the graphene layer in between. And this technique goes back to Eisenstein and others in the early 90s applied to 3-5 semiconductors. So just to show you, what happens in bilayer graphene, I sort of set this up to say bilayer graphene looks good. Well, we can make these types of measurements, and we can see that as a function of the displacement field D, when you put a large displacement field here, you see a very high penetration field capacitance, and then you see these spikes, and these spikes are precisely those 1/√√ Van Hoff singularities. So that looks good, but there's no signature. We've never found a signature of ferromagnetism in encapsulated Bernal bilayer graphene in this regime. And so the hypothesis that I want to start with is the question is essentially whether this is not a matter of the physics is wrong or this prediction is wrong, but rather that the Stoner criterion is some number, and one needs to have a density of states at high enough density, and an exchange coupling that's sufficiently big to do what you want, to have the system become ferromagnetic. And so it's a matter of degree rather than of kind. And so an idea that we can start with, anticipated in these recent papers from both Jeannie Lau's group and Andre Geim's group, is that rhombohedral trilayers and multilayers may be the right approach. And so the reason for that is that unlike in Bernal stacked graphite, once you go from AB to ABA, the electronic structure changes rather completely. But in rhombohedral graphites, roughly speaking, the Hamiltonian stays kind of similar in that the most important sublattices are located on the outer layers, and all of the other sublattices are strongly hybridized, and so there's some suppression of the wave function weight on the other sublattice. So out of the six atoms in a unit cell of ABC trilayer, most of the wave function is concentrated on two atoms which are on the outer layers. And what this amounts to in a very simplified two-band model is that rather than getting, say, a p squared dispersion, you get a p cubed dispersion without applying an electric field. And once you apply an electric field, you actually get a p to the 6th dispersion, and that gives you a stronger Van Hoff singularity than you do in bilayer graphene. And so one might hope that this would give you stronger interaction effects. So it turns out, just again, a note to the experimentalists, of which I see a number in the crowd, this is rather difficult to do. In particular, ABC is quite metastable. It likes to relax to ABA. There's some tricks that we've developed that we'll put in preprint that we should release relatively shortly on how to do this in a way that at least is compatible with a reasonable device yield and allows us to incorporate these devices into the fully graphite gated and boron nitride encapsulated structure that we want to make everything very clean. But it's possible to do, and it has this great advantage that ABC is metastable. It's not unstable. So what tends to happen is that either ABC survives to the end of your fabrication process, or it converts into an ABA structure, in which case the device is not useful. So so you get one or the other, but what you don't get is sort of microscopic mixtures of the two. You might get a domain or two, but mostly it stays the same. So so this is what data look like. So again, this is a measurement of the penetration field capacitance, where using our knowledge of geometric capacitances in the device, one can plot it as the inverse compressibility in basic units. And this is a very featured plot. There are many things here. There's more than I am going to tell you about in this colloquium, but I want you to focus on several key features, in particular on this right-hand side, which corresponds to electron doping. I want you to focus on these sharp blue features, which correspond to negative compressibility, right? And which I'll try to convince you are actually a sign of exactly the ferromagnetic phase transitions that in a sense you would expect in a high density of states, low density material. So in particular, this is what they look like. So if you take a line cut from this data at 0 electric field applied, so this is where the band structure does not have strong band edge Van Hoff singularities, you'll find a little step, which is something that we understand from the band structure, but basically the compressibility is always positive. But when you take a cut at a high displacement field, you'll find that there are many regions of negative compressibility. That's beyond single particle picture. It is exactly what you'd expect when you have a phase transition between states that have a different electron density. And you can compare this to similar measurement in Bernal bilayer graphene, and there's nothing like this level of structure. So one way we can try to probe what's going on is to look at quantum oscillations. This is a typical way to probe the degeneracy of the Fermi surface. And so we can take measurements of quantum oscillations in this first regime here on the left of this phase transition, the second regime, and then out here in this high density regime. And what you find generically is that the degeneracy of quantum oscillations in, let's say, this regime indicated by the white star is a half of that in the regime indicated by the yellow star, and is a quarter of that indicated in the regime indicated by the blue stars, which basically tells you that the degeneracy of the Fermi surface in this region is one-fold, two-fold, and four-fold, respectively, exactly what you'd expect if you have sort of a cascade of ferromagnetic phase transitions. So we can label these 1x, 2x, and 4x. It's particularly simple on the electron side, and so I'll focus on that region. The reason for that is that the density of, once you do a proper accounting of the band structure, the low density band structure is somewhat more complicated than what I showed you. You have to take into account, various hoppings within that unit cell. And what you find then is that, for electron doping, the density of states is essentially peaked right at the band edge and then decreases and has a relatively simple structure. Whereas for holes, there's a considerably more complicated structure at low density. That's what leads to this complicated stuff for hole doping, which I won't discuss here. But instead, we can focus on, electron doping, and we can focus on just trying to understand whether basically density of states is going to tell us, in the Stoner picture, the only thing that enters of the electronic structure of the material is the density of states. You more or less assume some phenomenological exchange, and then the rest is essentially single particle physics. And it's a crude model. It doesn't take into account many things, but the basic prediction is that Stoner ferromagnetic transition should follow the behavior of density of states. And the behavior of density of states we basically know because we basically know a lot about tight binding models in graphenes. So modulo some adjustment of parameters, we understand the basic electronic structure. So the question is whether you can take this type of model where this is the energy and as a function of how much you occupy these different flavors. So alpha here index spin and valley flavors. We can start by just saying spins and valleys are all the same. That's not really true, but we can say that they're just an index, which spin and valley projection you choose, and then see what this model gives us. And so we can see, so here's a comparison of experiment in ABC trilayer graphene and theory, and what you can find is that you have indeed a very similar structure. So what's being plotted here are one-fold, two-fold, three-fold, and four-fold degenerate Fermi surfaces. The qualitative feature of this displacement field versus density behavior are indeed captured. You can see that these transitions follow this kind of trend. That apparently is simply following where the density of states is high. And so that lines up. You're basically seeing the fact that as you go to larger and larger displacement fields, this Van Hope singularity gets bigger and bigger in terms of how many electrons it can contain at high density of states. And so your magnetic transitions move out to higher and higher density. Interestingly, and I won't dwell on this, this model that does not seem to capture the correct number of transitions. So in experiment, we see a one-fold degenerate Fermi surface, a two-fold degenerate Fermi surface, and a four-fold degenerate Fermi surface. But so far, it has been very difficult theoretically, including doing more sophisticated Hartree-Fock type calculations to eliminate this tendency of the models to give you a three-fold degenerate Fermi surface, which is sort of an outstanding puzzle. But basically, we can take our experimental data and understand that what we have is at zero magnetic field, we have apparently full spin and valley polarization in this one-fold state, 2 out of 4 flavors occupied in this two-fold state, and then a restoration of spin and valley symmetry this fourfold state. It turns out from tilted field measurements, you can understand something about the nature of this spin and valley order, where you see that as a function of in-plane field, this boundary between the fourfold and twofold degenerate state is strongly dependent on in-plane magnetic field and cusped, which tells you that there's a difference in spin polarization between the twofold state and the fourfold state, but there's no such feature between the onefold and twofold state. So we can tentatively ascribe the symmetry breaking to say that this is onefold degenerate state is spin and valley polarized. The twofold degenerate state is spin polarized and valley unpolarized. And then, okay, the fourfold state has to be totally unpolarized. And this is borne out by the dependence of the resistivity on in-plane field, where you see sharp features as a function of in-plane field in the onefold and twofold state, but no in-plane magnetoresistance in the fourfold state. That's, again, consistent with having some type of spin physics and domains in these one and twofold states, but not in the fourfold state. So what do we want to do, right? So where can we go from here? We have this basic notion here that we now have this itinerant ferromagnet. This is all metallic physics, right? You have fully polarized, maybe fully spin and valley, and in another case, fully spin polarized Fermi surfaces. They're itinerant magnets. There's many interesting things one can do with itinerant magnets in the direction of spintronics and so on. But for many of the things that our group is interested in particular, you know, let's say relatives of quantum Hall states and topological insulators, we like gaps. Gaps have well-defined quantized properties. And in this case, where you have no moire, the only place where you can logically get a gap state is at some commensurate filling of the lattice, which, you know, within accessible density ranges is really only at the charge neutral point. So that's a rich subject of what happens at the charge neutral point. I'm happy to discuss what we've seen so far in these rhombohedral graphites and otherwise. But if it were more spectacular, I guess I would be showing it to you. There's a solution to sort of enrich this phase diagram, which is to add a hexagonal boron nitride layer that is aligned rather than misaligned, and create a moire pattern. And of course, you know, everything I'm going to tell you about in the next, you know, section of the talk was anticipated in papers from Feng Wang and from David Goldhaber Gordon, who studied the system. What we've been doing is trying to clean up the system by using graphite gates and doing bulk measurements like capacitance to try and understand this phase diagram better. But I should give credit where it's due. We were certainly inspired to get into this by that, by those works, many of which we've corroborated, some of which we haven't. So now once you have a, so, you know, the basic picture, right, is that when you align a hexagonal boron nitride and graphene, you generate a moire pattern of, you know, wavelength around 15 nanometers, and now you have many commensurate fillings. Anytime your density is some rational number multiplied by the number of electrons to fill a single moire, you in principle can get a gap state once you have electron-electron interactions. So we can try to understand, you know, the basic physics by just comparing our no moire sample, right, which is already rather complicated, right, of course, with a moire sample, which is extremely complicated, right? There's lots of stuff going on here. And I remind you that here what's being measured is the inverse compressibility. So where you see, you know, high on this scale, so yellows and reds, especially yellows mean gap states, you know, blacks, blues, and reds mean metals, thermodynamically speaking. So you can see that comparing no moire and moire, there are many of the same features, right? In particular, you know, let's say at low displacement fields, there's very little difference save for the appearance of a gap state at 4 holes per superlattice unit cell in the moire sample. But there are some other key features, which are in particular that there now appear also gaps at 1 and 2 holes per unit cell, right? And so the picture is relatively clear when you think about it. So this is a sort of schematic of the physics and where we have broken symmetry states with no moire. And what we can see is that you get gaps in a moire sample whenever you had a broken symmetry state without a moire. Now you turn on a moire, and if you had a one-fold degenerate Fermi surface, you will get a gap state at 1 hole per unit cell. if you had a two-fold degenerate Fermi surface, as is in here, you'll get a gap state, two holes or 2 electrons per unit cell. You won't get a gap state, for example, if your two-fold degenerate Fermi surface is at one electron per unit cell, right? You need to actually find something that is commensurate with the symmetry breaking. But the interesting finding here, which was a bit of a surprise to us, is that the nature of the magnetism and the isospin symmetry breaking in these types of systems is really there to begin with. It's been there all along in ABC trilayer graphene. The Moiré pattern, what it does is it gives you gaps at commensurate fillings. And I think part of the reason for the history of the field such as it's been is that when you measure transport, it is really very much easier to tell that something interesting is going on if you find a state with a gap. That's relatively unambiguous. Actually understanding the transport phenomenology, again, something I can't discuss in any detail in this talk, of either with a Moiré or without, is much more complicated. It's much harder to tell when you have something interesting. One of the advantages of measuring thermodynamic quantities. So one thing I want to focus on, which will be the focus of much of the rest of the talk, is the possibility of Churn insulators. So it's been since the several years, it's been understood that when you have every graphene heterostructure has starts off from the Dirac points of monolayer graphene, and when you gap a Dirac point, you generically generate Berry curvature, and that Berry curvature summed over a band can generically be non-zero and give you a finite Churn number for that band. There's a restriction from time reversal symmetry, which is that the Churn numbers in bands in opposite valleys better be opposite to each other, because the total Churn number better vanish if you have time reversal symmetry. But here you already have the basic ingredients, which are, even without a Moiré, which are that you have states which are valley polarized and spin polarized. They must break time reversal symmetry already. So it's entirely plausible to get finite Churn numbers at zero magnetic field. And if you get finite Churn numbers at one of these Moiré gaps, you generally expect to have some quantized anomalous Hall effect. So we can look for that using in these thermodynamic measurements by using this Wannier relation, which tells you the relationship between the density at which an energy gap is observed and the magnetic flux at which it's observed. And those are related by two quantum numbers, which are T and S. In a non-interacting picture, those would be integers, but once you have interactions, they can easily be rational fractions. And T encodes the Churn number of the bands, and S encodes basically the block band filling. Sorry, ignore these numbers. They're grabbed from later. So so we can take a look, for example, up at in this regime of high positive displacement field, and we can track this gap at 2 holes per unit cell, or this gap at 1 per unit cell, and we find that they simply don't move in density as a function of magnetic field, which tells you that they're topologically trivial gaps. In contrast, if you do this at large negative displacement field, you can find that the, for example, the gap at 1 hole per unit cell actually has a finite Churn number. It goes all the way down to 0 magnetic field. You see a gap with a slope is the strongest gap, and in the 0 field limit, you find that, in fact, you have some Churn number of 2, apparently, which is something that you can get out of the slope of this gap as a function of magnetic field. The density, slope of the density where the gap is observed as a function of magnetic field basically tells you the Churn number. It also should imply the quantized Hall conductivity of that gap. And when we measure that Hall conductivity, we find that it indeed is rather close to a quantized value. And this is comparable with the observation last year from Feng Wang and collaborators that in fact, in the same filling, you have some Churn number of 2 and rather nearly quantized Hall conductivity at that filling once you apply a magnetic field. There's an interesting fact, which is that the magnetic hysteresis actually observed in the system is rather weak, and there's not a quantized anomalous Hall effect. Rather, there's sort of a suggestive, you could call it a Churn insulator that seems to be going all the way to low magnetic fields, but doesn't quite quantize at 0 magnetic fields. This is a question I'll return to, and I think will be something that we can hopefully start to address. But one thing I just want to point out is that, essentially what this is telling you is that the Moiré minibands with finite Churn number, indeed, you can valley polarize them and you can get a finite Hall effect essentially in the zero field limit. But there's a question of, what is going to pin such a magnet? Because ultimately the pinning of these magnets is what controls magnetic hysteresis. And that's something that could be in principle very different in graphite versus any number of other systems which are magnetic, of which many have been studied, but this is something that involves anisotropy and disorder and many other things. So let me just show you a few more things in the zoo that you get here before I move on to a different type of heterostructure. So in particular, if you now look at this same Moiré structure over a much larger range of displacement fields, you can find regions where you actually have gap states, not only at integer fillings of the Moiré, but a variety of fractional fillings, and including, a quarter of an electron per unit cell, a third of an electron per unit cell, a half an electron per unit cell, two-thirds of an electron, and so on. And in particular, you can also find Churn insulators, so incompressible states that have apparently a Churn number, an integer Churn number of 1, that seem to compete with these types of fractional filling states. So it's not entirely clear the right microscopic description here, whether you should think about this as a Landau orbit in a pinned Wigner crystal or simply a competing Churn insulator that's very close. But it's interesting that these types of states seem to go almost to zero magnetic field. They're clearly not the ground state at zero magnetic field, but they're getting awfully close. These are some type of state that is a Churn insulator, so it has a specific relationship between charge density and flux, and but also breaks the superlattice symmetry by, say, trebling the unit cell. Okay, let me change topics a second and try to get back to this question of pinning and pinning of orbital magnets and whether we can achieve quantized anomalous Hall effects, changing to a different system. So this is twisted bilayer graphene. So twisted bilayer graphene is a bit different.
Sorry.
Yeah, sure.
Andrea, just a quick question. So do you understand what is the structure of the states at fractional filling? Are these something like a Wigner crystal or something like that?
I expect that they're Wigner crystals of some kind. I am more confused by these Churn insulators that seem to be competing with them. I think, the fact that one sees them at there's been lots of work on TMDs recently that show very beautiful sequences of these Wigner crystals. I expect it's very similar to that. And also it's in a regime where the bands themselves are not topological. So I think physically it's very similar to the case of TMD heterostructures where Wigner crystals seem to be the dominant ground state, but I'm less sure about what's going on with this sort of competing Churn insulator and why that would be happening. That seems kind of interesting.
All right, thanks.
Yeah, sure. Right, so changing topics to something that is closely related but not microscopically identical. So in twisted bilayer graphene, I believe everybody is familiar with the underlying physics, but a flat band is generated a little bit more out of nowhere in the sense that there's this resonance condition between interlayer hopping and the twist angle that allows you to flatten and isolate a flat electronic band. The end result is in many ways similar to what I've told you about, in that you generate an isolated flat band on this Moiré lattice, which may have non-trivial topology, and that's what I'll focus on before. Of course, in so much as brief history, the last years have seen, identification of this isolated band, identification of strongly correlated physics, meaning insulators at fillings that are not within the single particle picture, similar to what I showed you in ABC Moirés, superconductivity, and in particular ferromagnetism, which is the thing that I will tell you about in the most detail, which appears to show up, and as you can see here, is considerably more robust in the sense of hysteresis than what's been seen in, for example, ABC trilayer graphene, and this is work from Goldhaber-Gordon group. So our work here is, nothing. There's no great genius here, but we were able to make devices that were somewhat cleaner. A key element is to have the twisted bilayer graphene aligned to the hexagonal boron nitride. Of course, I think we now try to do this and persistently fail. When this succeeded, it was because we weren't trying. But it turned out we made one that was aligned, so you can see crystal axes between boron nitride and the twisted bilayer were right at 30 degrees, suggesting that you could have alignment. And in this case, the single particle physics is to have, again, isolated flat bands within the two different valleys, which have opposite Churn number of 1 per spin, and so 2 or -2 when you include the spins. And the basic observation here is, and now this is transport measurement, I'm showing you Rxx and Rxy plotted as a function of charge carrier density, or on the top axis, filling of electrons within this flat band, that at 3 electrons per unit cell, one finds a nearly quantized Hall effect and a nearly 0 longitudinal resistivity. It turns out that if you are careful about your measurement and deal with some issues arising from bad contacts and so on, and perform magnetic hysteresis measurements, actually that quantization is extremely precise, as is the vanishing of the Rxx. So in particular, you see this hysteretic transport, quantized anomalous Hall effect, and which is quantized to essentially a contact resistance limited fraction of a percent, and large discrete Barkhausen-like jumps in both Rxx and Rxy. So again, it looks similar to an AC on B, and it looks like you have some number of flat bands with finite Churn number. Those Churn numbers vanish in the two different valleys, but by virtue of the strong interactions, apparently the system favors polarizing into one valley, giving you a net Churn number and an energy gap at a commensurate filling, in this case 3 electrons per unit cell. Of course, the details of when this occurs or doesn't occur at what given filling, this has been explored a fair amount since then, highly sample dependent, probably depends on a lot of different parameters, but this is apparently one way to do that. It's instructive to look at the energy scales as a somewhat of an aside. If you look at activation energy extracted from transport, you get something on the order of 30 Kelvin, whereas the Curie temperature of the magnetism is much smaller than that, actually something like 7.5 Kelvin. That's quite unusual by the standards of, quantum anomalous Hall effects were discovered already 7 or 8 years ago in a very different type of system. So chromium doped bismuth antimony telluride, which is essentially a magnetically doped semiconductor. The semiconductor is a topological insulator that has strong spin-orbit coupling, but the combination of magnetism and spin-orbit coupling give you a gap. The magnetism in that system is quite robust because it's the magnetism of these chromium or iron or other dopants that people have used. You get a Curie temperature of something like 15 or 20 Kelvin, but then an energy gap in the electronic system of only a couple of Kelvin. So in other words, the Curie temperature is really the stronger effect, and only a little bit of that gets into your electronic system, and disorder may limit that further. In twisted bilayer graphene, we find instead a Curie temperature, on the order, this should be 7.5. It depends how you measure it, of about 10 Kelvin, and then an electronic gap that's several times larger than that. So that's sort of more suggestive of a clean system, in particular, to the extent that we've been able to compare this with quantitative theoretical models. This seems to be more or less in line with what's expected. And the mechanism is, again, very similar to in twisted bilayer in ABC rhombohedral graphene. You have gap Dirac points. That gives you some finite Churn numbers. You have no spin-orbit coupling, but now you have anisotropy that's coming from the fact that these are valley orbits, and that's what allows you to have an Ising-like magnetic system. And interactions happen to favor, for a given filling, full polarization into one of these orbitals, which generates a net Churn number and a quantum anomalous Hall effect. But a key difference, which is just empirical at this point, is that in twisted bilayer graphene, this pinning is very strong, whereas in ABC trilayer, it does not seem as though that pinning is very strong at all. So where is that coming from? So what I'll show you is that we think it's basically tied to structural disorder, and I think that may be suggestive of how one can control it in the future. So in twisted bilayer graphene is made by this, everybody makes it by this variation of these sort of pair and stack methods that I think were first reported by Emmanuel Tatouk's group, where you basically are taking 2 graphene layers and plunking one on top of the other. And nothing is structurally, no structural ground state or metastable state exists that tells you that 1.1 degrees is somehow good. You're going to quench whatever strain you have. And so everybody works very hard to try to decrease this amount of strain, but it's inevitable that it's there. And in fact, when this has been imaged with high resolution, one finds, twist angle disorder of on the order of several hundredths of a degree, which is a lot in this system because the band structure is exquisitely sensitive to that twist angle. So across even a couple micron device, you see pretty large variations in the twist angle. So in order to try to understand what was going on in these systems, we decided to try to image them. So in particular, you need a very sensitive imaging technique. So the moment densities you expect are on the order of a Bohr magneton per electron, which means a Bohr magneton per superlattice unit cell. That corresponds to effectively a current, because 2D magnetization has the units of current, of 50 nanoamps, which is hard to detect magnetically. If you're, let's say, 100 nanometers away and you want to do things with that resolution, you're going to get 100 nanotesla. But there exist techniques, in particular nanosquid on tip microscopy, which was developed by Elie Zeldov's group, where I spent some time, and we have built up in our group, kind of fits the bill. It gives you the right type of sensitivity. You can get tips, depending, there's some tuning to do, but you can, for a tip of 200 nanometers, we're using indium in the experiments I'll show you, you can get a magnetic field noise on the order of, 15 nanotesla per root hertz, which is what you need to do this and operate in the appropriate regime of temperatures and magnetic fields. Just a brief technical aside. I know I'm sort of saying many things in this talk, and please feel free to interrupt or just to ignore this if you're not interested in the experimental details. But the data I will show you is taken using this essentially gradient magnetometry. So we have our tip coupled to a tuning fork, and that tuning fork oscillates at 32 kilohertz. And that allows us to measure the squid response at a frequency well above the 1/f noise. The price we pay is that we don't actually sense the magnetic field. We rather sense the derivative of the magnetic field as a function with respect to the direction that the tuning fork makes the tip oscillate. This is all calibratable. So here's actually our calibration. This is actually a thermal signal. It's not important too much the details, but if your DC signal looks like this lower left, then and your tuning fork signal looks like this, you can find exactly the angle and amplitude of that by comparing that to a numerical derivative of your DC signal. And so you can calibrate that. But the images I'll show you, for example, here are measured in this mode where we're measuring the magnetic field at the frequency that the tuning fork oscillates, which generates an image that tells us the gradient along the direction of the tuning fork, which in this case runs sort of lower left to upper right. So to do this measurement, we're looking for a small signal. There are other experimental backgrounds that we have to worry about. What we do is we measure at the same magnetic field, but on different trajectories within this hysteresis loop. And this produces images like this. And you can see if you have the patience at this point to compare them in detail, you can see that they're more or less opposite reversals of each other. And so you can actually take half the difference, and that'll generate this response, and you'll see that in fact there's a fair amount of structure in this in the magnetic signal coming from a fully polarized orbital Churn insulator. This is done at nu equals 3 at about 1.5 or 2 Kelvin, and so you can see there's a fair amount of structure. It turns out that using Fourier, sort of typical Fourier techniques, from once you know the derivative with respect to given vector everywhere for a 2D sample, you can use Fourier domain techniques to then extract the actual magnetization. Many careful calibrations later, one can find that, in fact, the peak magnetization density is on the order of 4 Bohr magnetons per superlattice unit cell. So that's actually somewhat comforting. It's telling you that it's largely an orbital magnet. You would expect the spin magnetization here to be no more than 1 Bohr magneton per unit cell. So this is almost entirely an orbital magnet, if not entirely an orbital magnet. But the thing I want to show is sort of our investigations of these domain dynamics and how they are pinned. So in particular, what you can do is take images at not only on the major loop, but also, let's say, on a minor loop here. So at position D, where you've stopped and prepared your system at, let's say, close to 0 Hall resistivity, and then you can take images at both at each of these points. So for C, D, and E points are plotted here, And now you can look at differences, pairwise differences between, let's say, E minus D and D minus C, which tell you that which domain has flipped between C and D. We can look at that here. And you can see that about half the sample has flipped. This orange blob is the domain that has flipped between these two. This orange blob is the domain that then flips to get you to E. An interesting fact, which we discovered over many, many attempts and many broken tips and many broken wires in doing this, is that every time we cool down the sample, this domain pinning stays in the same place. And recently, we're working on trying to correlate this more tightly with twist angle disorder. It doesn't seem to be perfectly correlated with twist angle disorder, but it certainly seems to be correlated with structure. And if you think about these systems, they have two graphene layers, which are nominally aligned, and then a graphene and boron nitride layer, which are nominally aligned. And there are a lot of interfaces whose angle you care about, and that may be complicated. Certainly, there's some theoretical work that suggests when you get when the ground state is magnetic depends strongly on all of those things. However, the empirical fact is that it does not change from cool down to cool down and is always in the same place. It is not a spontaneous thing. This is clearly something that's pinned to structure. So it seems as if this strong pinning that we see here really arises from the disordered nature of these twisted bilayer samples. Now, we have yet to try to control this deliberately. I think that that is a very exciting direction, for example, in these ABC structures, to try and introduce disorder and pinning centers and other things that might actually allow you to control that pinning. The reason for that is that once you have this type of strong enough pinning that you can actually stabilize these magnetic states relatively well, there are a lot of enjoyable games that you can play with these types of structures. In particular, the pinning may be strong here in the sense that you can stabilize these states indefinitely, but it's not so strong that you can't overcome it with various knobs. So I'll show you one, which is current-induced switching. So this was done in twisted bilayer graphene in this same device that I've shown you. And by tuning the temperature to be not too far from the Curie temperature, you can actually get your magnet to switch with essentially negligible currents. But despite that, it's completely non-volatile. So for example, you can use little current pulses of a few tens of nanoamps to switch the magnetic moment of your sample, presumably in the one remaining domain at 6.5 degrees between pointing up and pointing down. And you can read that out with the Hall effect. Actually, the mechanism for this is something that there have been a number of theoretical proposals for this, something we're trying to investigate with real space imaging in the future. But that's just an example. I mean, this is of course something that you can do with other spintronic type devices, but here these threshold currents are extremely small and otherwise relatively straightforward to control. Maybe I want to tell you in the last, how much time do I have, Anton? I can stop or I can keep going a little bit longer.
So we have like 1.5 hours for the whole thing, but this is including preferably plenty of time for questions. So 15 minutes easily.
Oh, fine, no problem. Okay, good. I'm going fast then. That's good. I'll get to everything for once. Right. So I told you something about pinning and disorder. I want to tell you a different modality to control these, and that arises from the basic fact that these, we believe, are largely orbital magnets, right? In other words, our the claim from the theory literature, and I'll try to substantiate with experiments, is that the magnetization that we see and the magnetization that is relevant for all of the physics is either entirely or largely coming from orbital physics. And so, as you can look up in kind of modern theory of Barry phases and magnetization, will relate that that magnetization to that orbital magnetization to two contributions. There's a contribution effectively from edge states and Barry curvature, and there's one from the rotation, the angular momentum of the block wave packets themselves. But the basic point is that all of these are density dependent, right? And depend, of course, on the band wave functions themselves, which, as I think I've shown you in various ways, you have a great deal of control over in these systems. And more importantly, when what our measurement this total M shows is that this is, if not the only contribution, certainly the dominant contribution. So this is something that, whereas, if you want to reverse the G factor of an electron, you can do it with spin-orbit coupling, but you can't really do it controllably. It's kind of, you have to do a lot of work to do that. Here, the sign of this is an arbitrary function of the band wave function. So in principle, you can play with also moments of both signs, and you can have large contributions from edge states or from bulk states. It's all something that is tunable, and all will be density dependent. So actually, we can look at this with the squid already. So here is just a plot. We're taking a line cut of this tuning fork signal as a function of electron density, and just doing that measurement over and over again. And we can try to extract some figure of merit for how strong the magnetization is. This is actually the very last measurement we took in March before we unfortunately had to shut down the lab, as I'm sure many in the audience will sympathize with. So we have not been able to get back to do this more quantitatively, but luckily we got this. And what you can see here on the left axis in white is essentially the strength of that tuning fork signal. And plotted in blue dots is the size of the anomalous Hall effect. And what you can see is that they're not exactly the same, right? In particular, everywhere that there are blue dots, that means there is some hysteresis. And you can see that there is, first of all, an onset of magnetization that is quite large, well before the hysteresis becomes, close to quantized. And then once it is quantized, there's actually a rather dramatic collapse of the measured tuning fork signal inside that quantized anomalous Hall gap. So if you look at this formula, actually, it turns out that when you're inside a gap, you're not adding any electrons, and rather all the contribution comes from this chemical potential dependent part. And that chemical potential dependent part basically just measures the Churn number. So you expect in these systems a change in magnetization when you cross a Churn insulator gap, as this is, that is simply the Churn number times the size of that gap divided by the flux quantum for units, okay? And there was this beautiful point that was pointed out by Alan McDonald's group right around the time we were doing these measurements, that actually in these orbital Churn insulators, this is an effect that's in every Churn insulator. It's in any quantum anomalous Hall state. It's generic to any lambda level. It's an old piece of physics. What they pointed out was that because these other magnetization contributions are small, this can be dominant. Indeed, it can even completely cancel what you might call the bulk contributions from the wave packet rotation or energy bands. So, so we believe that actually is a relatively straightforward interpretation of this data, which is that your magnetization is very small when you're hole doped relative to this Churn insulator gap. When you enter the Churn insulator gap, you get essentially magnetization of edge states. And then as a function of additional density, you know that by the time you get to full filling of the band, this must go back to zero. You're now filling bulk states, and that's reducing your magnetization again down to zero. Interestingly, there are regions where the transport is hysteretic, where at least within the experimental resolution of our probe, you have zero magnetization, presumably because these orbital moments are very small. To show you, and it's what I'll end on, I think the most spectacular manifestation of that type of physics, I actually want to switch one more time experimental systems to a close relative of twisted bilayer graphene, which is twisted monolayer on bilayer graphene. So this is a monolayer twisted with respect to graphene bilayer. And this is what the phase diagram looks like as a function, for a given angle. This is, I think, 1.25 degrees, as a function, again, of displacement field and of charge carrier density. And you can see that for certain choices of the displacement field, you can have a gap, a high resistivity state at charge neutrality, also at 4 electrons per unit cell. And then you can have what look like correlated insulators at 1, 2, and 3 electrons per unit cell. And I should point out there's, this is sort of somewhat related to double bilayer graphene, which was studied relatively extensively recently. And there are several, 2 other papers that appeared around the same time from Manchester and University of Washington on this type of system that are also, find sort of similar results in terms of this basic phase diagram. what I want to show you is that this is also an orbital Churn insulator. So in particular, at nu equals 1 and nu equals 3, one finds nearly quantized. They're not perfectly quantized, although once you've seen the magnetic images that I showed you from our microscopy experiment, I feel like you should be shocked that any of these are ever quantized. I feel like the level of actual structural disorder and its interaction with the domains makes it rather a miracle if that this worked at all, even once. But they're relatively close to being quantized at around half h over e squared. So that is consistent actually with what one finds by the magnetic field dependence of these strata slopes, which seem to indicate a Churn number of 2 at nu equals 1 and nu equals 3. And that's actually consistent with band structure, which suggests that the Churn number of the single particle bands is also 2. So these look like Churn number 2 quantum anomalous Hall states, right? But the thing that I want to point out, which was really very confusing to us for a while, is this behavior near nu equals 3. So when I first saw this, my postdoc, Gregory Polshin, showed it to me, and I sort of said, this looks like you have a cable that's not well connected or something like that. But it's not true. It's actually real. So what you're looking at here is the Hall resistivity, and it's as a function of density. And the way these are, it looks very noisy. It really looks like you have some problem with your fridge wiring. It still looks that way to me, but it's generic. It happens all the time. And in particular, what you see is actually that the Hall conductivity changes sign as a function of charge carrier density very abruptly at finite magnetic field. And everything in general is very noisy, right? It's very hard to actually control this and get, if you measure this again, you'll find that all of this is sort of slightly different. The switchy behavior turns out to be a real thing. In particular, there seems to be hysteresis in not only as a function of magnetic field, but also as a function of just the DC gate voltage that you apply. So what I'm plotting here, hopefully in not a too confusing way, is the Hall resistivity as a function not only of magnetic field, but also for some small finite magnetic field as a function of the applied gate voltage, which I've translated to charge carrier density, although it's probably, I should just say it's gate voltage. And you can see that you can actually irreversibly switch the magnetization as measured by the Hall resistivity using a gate voltage rather than a magnetic field. You can do either one. And this turns out to be very much in line with what I told you about before. So in particular, we know that as you dope your sample across a Churn insulator gap, you get a contribution from the edge states that is the Churn number times delta divided by phi naught. That's just a number. So now, what if M bulk is half that and of the opposite sign? Then what you expect is that you may be in the bulk on one side have a magnetization of one sign, and on the other side of the gap, you have a magnetization of the other sign, which means that as you cross the gap at a finite magnetic field, you go from being in the ground state with respect to the magnetic field to suddenly in the metastable state. And if your system has strong pinning, you may well sit in that metastable state until you overcome that barrier, relax, and so on. But by microscopically controlling that magnetization, it means you can basically make an electrically actuated switch for your magnetization, where you actually flip the sign of the magnetization up and down just using an electrical voltage. So you can see this again put to use in this sort of thing that we've, this is kind of the entertaining data we take after we've understood the physics. Here's again plotted the Hall resistivity, but now down here are our control knobs. So this is density, really it's just gate voltage, right? And magnetic field. And so you can see that you can switch the sign of this anomalous Hall in a non-volatile way, either by ramping the magnetic field, so you can ramp it so that it ramps to the so that it switches to the other state, or by a little excursion in the gate voltage. And so you can make this magnetic bit flip up and down just using a gate voltage, right? Every time there's a little red spike, what you've done is flip this magnetic bit. And the remarkable thing here is that unlike in the twisted bilayer, where if this happens, I didn't discuss it in detail, but if there's a sign change, it seems to happen in the middle of an energy band at sort of some random partial filling. So in an itinerant regime, here it's actually happening inside a quantized anomalous Hall gap. So what you're actually seeing is mostly edge state transport. There's some disorder, but it's mostly edge state transport. And you're actually flipping the chirality of those edge states with a gate voltage, which in principle means that you can do all the things that we know how to do so well in 2D systems, patterning gates and so on, and actually just control the chirality of quantum anomalous Hall edge states locally as you wish in a programmable way, if you can manage to make devices like this in any kind of reproducible way, which, by the way, we have not, but is presumably something that we'll eventually figure out. So let me show you just one very last piece of physics, which is that in this same system, and I anticipated this a little bit before in ABC trilayer, we actually start to see some new states. So Churn insulators at fractional band filling, and by fractional band filling here, I really mean rather than 1 or 2 or 3 electrons per unit cell at 3 halves or 7 halves of an electron per unit cell. So here's at 0 magnetic field. You can see these little features at 3 halves or 7 halves of an electron per unit cell. And if you look at these magnetoresistance plots, you can see that they seem to agree with having a finite strata slope, which tells you a Churn number of 1, whereas, as I told you before, at nu equals 3, you have a Churn number of 2. That's our switchy Churn insulator. Here you have something at 7 halves that has a Churn number of 1. That's consistent with what we call symmetry broken Churn insulators. So these quantum numbers that characterize these Wannier plots, you have this block band filling index, and obviously that's fractional, but you have an integer quantized slope. So what does this mean, right? We know there are Churn bands with Churn number 2 in this system. Everything is consistent with that. What this looks like is that when you go to half filling of such a Churn band, you open up a gap. Interactions are strong enough that you open up a gap at half filling. The interesting takeaway here is that apparently you partition the Berry curvature evenly between the states that are occupied and the states that are unoccupied, which needn't be so, right? So that if you have a band that has a Berry, especially in these Moiré systems, you may have a band that has a lot of Berry curvature, say at one of the extrema, and that's where all the Berry curvature is. And so if you go to half filling, nothing says that you should be able to split half the Berry curvature above and half the Berry curvature below. But here, apparently, either interactions are strong enough that they just prefer this type of state, or the Berry curvature is uniformly distributed in the band, probably not, or it's concentrated, let's say, at the band maximum and the band minimum, and so when you're at half filling, you evenly partition it. But the fact is that that seems to be what happens, and this is something that we've seen this type of state, these kind of partitioning of Berry curvature in Hofstadter bands at very high magnetic fields. There's originally by Corey Dean's group and later in follow-up work of ours. When you have high Churn numbers, these are a type of ground state called a symmetry broken Churn insulator, where you may double, in this case, the unit cell and break the superlattice symmetry. But we've never seen them at 0 magnetic field. And actually that, I think, is relatively important because here you have, hysteretic transport. There's clearly broken time reversal symmetry. You're really relying on 0 magnetic field physics and some magnetism, which is intrinsic, to make a relatively exotic type of Churn insulator that breaks this symmetry. And in particular, what we've seen in Hofstadter bands is that the general energy scales that characterize these symmetry broken Churn insulators are not very different from the energy scales that characterize fractional Churn insulators. So fractional Churn insulators are sort of really where we would like to go here, right? They're states that have fractional charge and fractional quantum statistics. They live on a lattice, and we've seen them in these Hofstadter bands. Let's say at partial filling of a Churn -1 or a Churn 2 band, you can see states that have a fractionally quantized Hall effect, but finite amount of charge bound to the lattice. And so I sort of think that this is kind of a good sign of making these at 0 magnetic field, which for us is a bit of a holy grail, because very much of what we would like to do is to learn how to manipulate fractionally charged quasi-particles and their fractional quantum statistics at, in any of these van der Waals heterostructures, work that I didn't tell you about today, but that is sort of a major focus of our efforts. Getting that at 0 magnetic field is, of course, convenient, but more importantly, in Hofstadter bands, all of this physics is really limited fundamentally by an energy scale, which is the Coulomb energy, which depends on the magnetic field. And there's just only so big you can make a magnetic field, and therefore only so small you can make the magnetic length that controls this. Realizing this in a lattice system opens up a lot of new things. In a Moiré system, it may not be so much better in terms of numbers because you have a moire wavelength that is not so different from magnetic lengths that you can realize, but it may be, and there may be routes to making this physics more robust in new experiments that one can do. So this is sort of, I think, where we are going with this basic physics. So here is, yeah, let me conclude and say that I think, you know, the basic takeaway we've gotten from this, which perhaps for us has been more a question of understanding, you know, what has been there in various ways for years already, is that there is sort of, you know, graphene wants to be an itinerant ferromagnet. It's actually not that hard to make it an itinerant ferromagnet once you jack up the density of states a little bit and reduce the disorder. Once you have a moire, it allows you to have gaps at non-zero density and sort of a variety of underlying bands that you can play with, including gaps that are magnetic, or rather, you know, once you have this magnetism and you make gaps, those gaps will be magnetic. They're fundamentally orbital magnets, and so they couple strongly to structural disorder. You can push them around with currents and electric fields. You can get these new types of knobs. And you know, I think for the future, an interesting thing to think about, which I would love to hear serious, you know, theoretical proposals to try and find, you know, what is the ideal system here to look for fractional quantum Hall effects at zero magnetic field, because we have topological flat bands. We know they often break time reversal symmetry. So, you know, what are the right details, you know, so that we're doing somewhat more of a guided search? I think that it's probably, there begins to be literature about that, but I think that's something that there might be some opportunity for also experiment and theory to work together in a more directed way. The details clearly matter, but the details are extremely, exquisitely, annoyingly tunable in these systems. And so, so one expects that there will be somewhere in this forest of parameters where this can work out. So let me thank by name in particular the main contributors from my group. So let me acknowledge Charlie, Gregory, and Marek, who worked on the twisted bilayer graphene, Gregory, who led the twisted monobilayer graphene, and Haoshin and Ben, who have been team ABC, and all the other members of my group, as well as our theoretical collaborators. And thank everybody for, thank all of you for having a listen.
Thanks, Andrea. I see already a question. Rudra, please.
Hi, Andrea. This was a great talk. Loved it. Could you please go back to the slide where you were showing data about locally measuring the orbital magnetism? Any one of those slides?
Yeah.
Yeah, this one is great. So if I understand correctly, what I'm seeing in the color profile is like a gradient of magnetic moment.
This is now magnetic moment.
I see. So you've integrated through the.
Yes, yeah, we've done all of that. Yeah, we've done all that. Yeah.
I see. So great. So my question is this: you had this little discussion about whether this is arising due to the edge currents, or whether this is arising due to the block wave function, you know, the atomic level structure. So if it's arising out of edge currents, you wouldn't expect to see this variation of the orbital magnetism through the material. Could you please comment more on that?
I disagree. I mean, you know, it all depends on the edge of what, right? And how much, you know, how much all of the, where's the formula? How much all of the terms in this, sorry, I've lost my place here.
I think it was there at the beginning.
There we go. Yeah. How you know, how much these different terms all depend on twist angle and registry to the hexagonal boron nitride and strain. And so, you know, I think the short, you know, answer is that it probably depends on all of them, but this huge change, you know, this order 1 change of the measured signal inside what is nominally the bulk gap, I think tells you that it's mostly edge currents. That, you know, most of this peak signal we see is edge currents.
I see. It's not. It's kind of that the size of that particular flip is, you know, more or less the same throughout the sample.
Roughly, yeah. I mean, that's what we would like
see.
to look at. We would like to correlate this closely with the twist angle and the alignment of the boron nitride, which I think we can do by very carefully mapping Landau levels locally, but we don't have that sort of comprehensive data set yet. It's a very good question, right? This data set has been hanging over our heads now for 9 months in terms of wanting to understand exactly how all of this is correlated and what are those pinning centers? What are these, you know, these inhomogeneities? What structural feature are they correlated to? It's clearly a structural feature. We do not know. Once you have a lot of inhomogeneity in your sample, M depends on every term in this depends on
Right.
On density, right, in a different way and position. So I think it's possible to understand that from experiment, but it's not something we understand now from experiment.
Okay, thank you.
Thanks for the question.
Hello, thank you for the talk, Andrea. I've got a question. You noticed in one of your slides, right, at positive displacement field, you had trivial states, but at negative displacement field, you had non-trivial states.
Yeah, this is
so
ABC.
what leads to the
Right.
asymmetry between positive and negative?
Oh, well, oh, yeah, sure. Great question. It's because the boron nitride is aligned on one of the two sides, not on both. So there's if you want, you know, as a simple starter, you could think about this Hamiltonian plus a periodic Hamiltonian that is proportional to a matrix that has a 1 here and zeros everywhere else. So it's just on one of the two layers. So the structure is layer asymmetric. You have unaligned BN, ABC trilayer, aligned BN. So basically, it seems like when you push the electrons to the layer, let me see if I can get this right. I think when you push the electrons to the layer next to the superlattice, you do not get topologically non-trivial bands, but when you push them to the opposite layer, you do get topologically non-trivial bands. It's either that or the reverse, but the asymmetry is in the structure itself.
Okay.
And where the superlattice potential is, yeah.
Cool, thank you.
Right, next question is from Hyun Mo.
Yes, so I have a question about ferromagnetism in ABC graphene. So as you may know, in conventional low density semiconductor, the ferromagnetic behavior depends on Wigner size radius known as RS,
Yeah.
which depends on effective mass and electron density. So could you give me a rough estimate of Wigner size radius compared to the effective Bohr radius in ABC graphene?
Infinity, because it depends on details, right? Because once you have this Van Hove singularity, I mean, at least the way, and you know, maybe somebody will correct me on this, but you know, close enough at arbitrarily low temperature and close enough to this, you have a divergence in density of states. So, you know, if you try to write RS in terms of density of states, you'll find that it's proportional to density of states, I think. And you can think about that as like the density of states effective mass that shows up in there. Well, the density of states effective mass here is gigantic. It depends on things like disorder, temperature, probably interaction renormalizations of the single particle band structure that presumably at some, you know, level more basic than ferromagnetism will reduce that density of states. So I don't really know, but very large, close to the Van Hove singularity, presumably.
So the band is perfectly flat, is that?
Effectively, I mean, yeah, if you have a divergence in density of states, you can say that, you know, effectively those are saying the same thing. Then it's a question of like, how are these other non-flat states actually mixed in, and as far as I can tell from my many conversations with many theorists, that's not a trivial question to answer. But I think that's the basic way to think about
I
it.
see. I have one more follow-up question. So if the physics is same, then all these ferromagnetic states at zero fields are Wigner crystals.
They should be, but although it's interesting, you know, here in principle, I think it should be very simple, right? The band minimum is just very flat, and I would expect you should have a bunch of Wigner crystal states, especially down here. Indeed, we see strong negative compressibility, what looks like a metal insulator transition, not totally clear. On the other side, it's less clear because the band structure is more complicated. It looks from Hartree-Fock that you might get nematicity. We haven't seen anything like that when we've tried to look for it so far. I'm not so sure. I think once you have a complicated Fermi surface and complicated density of states, I think somebody has to actually do the calculations. But there's a bunch of different competing states that you could get.
Okay, I see. Yeah, thank you.
Sure.
Yeah.
Andrea, I also have a question. Can you please show once again the gate hysteresis?
In which
the
system?
3D plot? I
Oh,
actually
3D
found
plot,
it
yeah,
quite.
the last thing, yeah.
Yeah, right. I found it quite profound and also puzzling. Yeah, this one. No, below, before. Yeah, this one. So, the 3D one.
This one is 3D, right?
Yeah, right. Yes.
Yeah.
So I'm wondering. So I sort of understand that if you have a magnetic phase and you start changing the density, you can cause a magnetization flip. That's fine. But at the same time, this is a symmetry broken system. So in principle, it should not. So I should be able to also observe the same curve, but with a flipped Churn number. So like because the gate sweeping is done at zero field.
The gate sweeping is done here at a slightly negative field.
So is it possible to change how the hysteresis is?
I think if you did this at slightly positive field, you would get would it be reversed?
Well, so certainly if there was no field, this would need to be symmetric, or at the very least, you would need to be able to find two variants, like two hysteresis curves.
Presumably tuned by current at that point, because I don't know. The problem with this system is that it's getting awfully multiferroic. So I understand what you're. Let me see if I can summarize your question, which is that you sort of expect some symmetry here, right? That if, at zero magnetic field, what chooses, you should be able to get a kind of symmetric curve somehow, right?
Or multiple curves.
Or multiple curves. Yeah, and I think the answer is yes. I think, from the point of view of, and that effect shows up as like absolute irreproducibility. It's very stochastic, and you jump between these different things that you could get when you're right at zero magnetic field, and things get a little bit, you want to bias it with something. Probably a current would do it. Certainly a magnetic field does it, in order to be able to use gate to control. We were somewhat obsessed with trying to control this in a way that you could do reproducibly. But yeah, at zero magnetic field, it's arbitrary. And so every time, every sweep you take, in a sense, will be different. And probably go to, the problem is that I think there are multiple domains, and there's some history dependence to which domain flips first, and that's stochastic. So there's probably many trajectories that one would have to map out. It would be better to just make a sample that was cleaner, and then I think exactly what you're saying would be possible. In reality, without a magnetic field, it's a little chaotic. What happens. Mm-hmm. That's my recollection. I mean, I should check with Greg.
Do you also know of any similar system where magnetization, where you can hysteretically control magnetization with density?
Not by reversing the sign. You can, certainly there's a long history in spintronics of figuring out how with a density to go from magnetic to not magnetic, or tune things between essentially zero and finite. But and that's also, I think, in some some of these 2D magnetic semiconductors. There's work where electric fields, you can turn magnetism on and off, or go between a ferromagnet and like a metamag, some sort of like layer antiferromagnet, but you can't switch it between plus and minus. As far as I know, this is the first instance of that, and I think for good reason, which is that you actually have to change the sign of the magnetization, and that's not that easy to do. I mean, now it's easy to do, but I don't know of any other analogs of that. I would love to hear about it. If so, we missed it, but we searched relatively carefully and did not find anything like that.
All right, thanks. I see no further questions. So thanks again, everyone, for joining, and thanks, Andrea.
Thank you.